Now let us discuss the big omega. F of n is said to be big omega of g of n if and only if there exists positive constant c and n naught such that f of n is greater than or equal to c times g of n for all n greater than or equal to n naught. Let's consider the same example where f of n is equal to 2n plus 3. Here 2n plus 3 has a lower bound of n. G of n is considered to be the lower bound. Okay. So here for all n greater than or equal to 1. So here f of n can be written as omega of n, or we can also write 2n plus 3 is greater than or equal to log n. So here log n is considered to be the lower bound of 2n plus 3 for all n greater than or equal to 1. Here we can write f of n is equal to omega of log n, or we can also write 2n plus 3 is greater than or equal to root n for all n greater than or equal to 1. Here f of n is equal to omega of root n. Now among these three functions, lower bounds of f of n, we can see that this function is closer to the given f of n, which makes more meaning to our conclusion. Now coming to theta notation, f of n is said to be theta of g of n if and only if there exist positive constants c and n naught such that c1 times g of n is less than or equal to f of n, which is less than or equal to c2 times g of n. When we consider the same example for f of n, where f of n is equal to 2n plus 3, you can see that here n is less than or equal to 2n plus 3, which is less than or equal to 5n. Here c1 is equal to 1 and our g of n is equal to n. And here c2 is 5 and g of n is equal to n. So here we can see that g of n, this function has a lower bound which is n, c1 times n, and which has a upper bound which is c2 times n. So we can say that f of n is theta times n, where the lower bound as well as the upper bound is represented with respect to the same time function.